Hi guys. In today's video, we are going to see what is binary search and how we can implement this binary search in our uh, questions. Okay. So let's talk about the agenda. So the today's agenda is what is binary search, why it is important, and we will see how we can implement this with the help of we have one question, which is very important question. Okay. And one more thing, important point here is the questions which I'm going to solve in the entire series is is very important. They are almost they covers each and every patterns. Okay, every patterns they are going to cover. So the questions I'm going to solve in this video, try to focus on this question and try to resolve this question by your own and try to understand this question as much as you can. So these are the very important questions. Okay, so let's get started. First question: what is binary search? Okay, what is binary search? So before proceeding, let's talk about the linear search. Linear search. Okay, so what is linear search? Suppose we have an array. Okay, array a sorted array 1, 2, 3, 4, 5, 6, 7, 8. Okay, and someone says find the value of this is your target. Okay, so if someone says find this value inside your array, so how you can find it? If it is found, then return true. If not, then return false. Right. So what is the linear search? It says the linear search says uh, iterate every element and check if it is present, if it is this value present or not. Okay. So right now your I is here. Okay, and you check if I is equals to a of I is equals to 8 or not, is equals to the target or not. If not, then you will move to the next element. If it is not, then you again move to the next element and you keep searching the element until you find the element or you reach at the last of the element, right? And if you found this element, then return true. If not, then you will return false. So in this case, you have to traverse till the end, right? So the time complexity will be O of n because you are traversing every element, you are iterating every element till the end. In the worst case, in the best case, you will always find the element at the first place, but the time complexity never consider the best cases. It always talks about the worst cases. So for the time complexity is O of n for the linear search. Okay. So to reduce this time complexity, we can solve this question using binary search. Okay. So in binary search, what we can do, we can reduce this search. Okay, let's talk about the target and search space. Okay. So in binary search, we need two things. First, we need target, and second, we need a search space. So the target is always required because if you don't have target, then um, you won't be sure like what needs to be searched. And if you don't have search space, then you won't be able to apply binary search. Even the linear search will also require the search space. Okay, so this is the search space. This is the search space. Now, uh, again, the same question. We can try with the binary search. What we can do? We can 1, 2, 3, 4, 5, 6, 7, and 8. Okay. Now, someone says find the value of 8. Okay. Find return true if you find it, else return false. Okay, make sense? Now, what you can do, you are here, okay, and somehow, let's say if you are here, let's say if you are here, then you have to iterate every element till that. But let's say if you are here in the middle of the array, in the middle of the array, and this is sorted, then if I say, uh, yeah, if you have to find this element, so where you find this element? You will always find at the right side of the array of the middle element. Why? Because this element is greater than the middle element, right? Because target is greater than A of middle element. Okay. But let's say if k equals to 2. So in that case, where you would look, what is your search space? So your search space is the left side of the middle element. So if target is less, then your search space is less than A of n, then your search space is left. Here your search space is right. Make sense? Now, in this case, you divided your array into half. Okay, you divided your array into half and you only processing this much element, right? So in this case, your time complexity reduced to O of log n. Okay, so that's why if see this time complexity is optimal, but if you have a better approach, then you will always proceed with the better approach. Make sense? Now, let me give you a real-time example, then we will proceed with the question. So the real-time example is, let's say if you have a dictionary, okay, and the dictionary contains A, B, C, D, X, let's say L, M, N, X, Y, Z. This is the dictionary keywords, or you can say that the letters. Let's say if you are in the middle, and not right now. Let's say if someone says find the value, find the word kite. You open the dictionary randomly and you land here M, or you land anywhere N. Okay, anywhere in the middle. Now, now if you want to search K, so where you would like to search, on the right side or on the left side? Tell me. On the left side, right? Because this is your target. And if your target is less, if your target is less than the middle where you landed, then you will always go to the left side. Then you will always search to the left side, right? You are not going to the right side. You can discard the right side. Okay. Now let's move to the question. Um, what the question is saying. Suppose you are having a sorted array. Okay, so this is the sorted array, and find the index of the target. So target is, this is the target K. It is denoted by K. You, if the target is not found, then return -1, and if the target is found, then return the index of the target. Okay. So this is the question. So the output value, this is K, and the output value should be 6. Answer should be 6. Now here, let's say somehow, but don't just think right now. Somehow you landed in the middle. Just think about this. This is your middle element, M element, and somehow you landed. We will see how we can land into the middle element. But just let's suppose if you are in the middle and you want to search this value 94. So in this case, target is greater than the middle element A of M, right? Is greater. If it is greater, so what was our formula? Our formula was we have to look to the right. So we will look to the right? Okay, make sense? Now, let me write here, and how we can now the question is, okay, let me write the cases first. Okay, case first. So case one is if, let's say, this is your array and this is your M element, middle element, let's say 21. If, let's say, if your target is whatever the target you have, if the target is A of M, if if you landed at the correct target, if you landed whatever the target is, then this is the happy case and you will return index, which is n. What is case 2? Case 2, if target is greater than the middle element, right? What we have to do? We have to, if the target is greater, then we have to move, search right. And if target is less than the value Whatever the target, if it is less than the value, then we have to look left. Then search space is left. Got it? Now let me let's dry run first, and then we will proceed with the final pseudocode. Okay. So k is, let me write, k is k is 94. We have a target is 94. So let me dry run first. We have we can start with here, and we can right now my low. Let me write low and high, not I and j. Low. This is lowest value index. This is highest index. So right now my lowest index and highest index, and we have to land mid, right? We need this lowest index and highest index to calculate the mid. Okay. And then case we have to find. We have to find search space. Search space. Okay. So this is the five columns. So right now my L is 0 index and my H is at 7th index. So mid value we can calculate L plus H divided by 2, which is 3. So my mid element, this is my mid element, is at this place. Okay. This is mid element. Okay. Now, if it is the mid element, now we have to check the case. Case one is, if case one, what is, let me write the case here. Case one is k is equals, target is equals to a of m. Case two is target is, what was the case two? Target is greater than a of m. And case three is target is less than a of m. Okay. Okay. Now, if target is this, then simply return the index. Return. If target is this, search right. If target is this, search left. Okay. So in this case, what was the target? Target is a 94, and 94 is greater than this 14. So 94 is greater than target is greater. So case 2 is applied here. And if case 2 is applied, then search space is right. And how we move right? Then we have to make our L from here to here. So L should be here. So right is search space and L should be m plus 1. We already have m, and m should be ahead, one place ahead of m, right? Now we have L is 4. We have H is 7. We didn't move 7. Now 7 plus 4 is 11. 11 divided by 2 is 5. Where is the m now? My m is here. Now we will again check if target and a of m. So again, target is greater than a of m. Second case. Second case. So if target is this, second case, then again we have to search right. And again, if we are searching right, then again we have to move L to the next of M. Then again L equals to M plus 1. Then L is 5. 7 H, we did L is 5. Sorry, L is 6, because mid is already 5. L is 6. So my L is here. So L plus 7, 6 plus 7 is 13. 13 divided by 2 is 6. Now A of 94 and A of 6. My middle element is here. So this is case 1, right? And if we have case 1, simply we have to return what we have to return, right? Okay. We didn't find the situation where we have to move the right element. So let's suppose if this was the case, let's suppose if this was the case, then we have to, if we have the search space left, then we have to move our H, and H should be m minus 1, because H should be placed before m. So this should be the case, right? Let me write a pseudocode, then you will understand better. Okay. So the pseudocode is, we have to initialize L equals to 0 and my H is at the last index. Okay. And we have to write a loop where L should be less than equals to H, because L should be less than equals to H means L should be max to max will be L and H should be the same place. Okay. If H crosses the L, let's say if L is here and H is also here. L is moving from here, H is moving from here. But if H crosses the L, that means we are duplicating our work, right? Because L has already moved. Now you are moving H to the L place. So that's why L and H should be equal. That should be the last condition. It should not cross, they should not cross each other. Okay. Now we have to calculate mid every time, L plus H divided by 2, because if we are moving, then we are calculating M every time. So M, we should put the M inside this. Now our first case was if target, that means K, equals to the A of M, then simply we have to return M. Else if K, target is greater than A of M, then we have to search right. And if we are searching right, then we have to move our L to the next of M. And else is the last condition where target is less than A of M. Let me write it for you, but you can skip. K is less than A of M. If this is the case, then we have to search right, sorry, left. And in that case, my H should be before M. That's it. My while loop ends. If not found, then we are returning -1. Solved. So this is the pseudocode. Now let's talk about the time complexity. And the time complexity of this code is O of log n. Why? Because we are dividing the array into half because of this condition. Because of this condition. This is a very important condition. And because of this condition, our time complexity is log n. Right? So that was the first question of binary search. And as we will proceed with this series, I'm uploading more videos on the binary search with more questions and more important question with me has easy, medium, and high level, and they will cover almost around 80 or 90% of questions you can do in lead code on or any other platform. Okay, so that's it for today. Please do like and subscribe my video, and we'll see you in the next video. Thank you so much.